about in-body stray neutrons produced in carbon and proton radiation therapy. Right? So this is my outline. Importance of carbon and proton radiation therapy, comparison of carbon and proton radiation, why we need to study about stray neutrons in this heavy ion radiation therapy, and then how did I validate my simulation results with the actual data, and then stray neutron dose equivalent per absorbed dose inside and outside the body. So first of all, you might know, sometimes you might not know that carbon and proton radiation therapy is some kind of an advanced radiation treatment method in the world right now. And you might wonder as to why. So let me explain you using this depth dose graph. It shows you how the dose, how the radiation release inside the body in photons, that means X-rays or gamma rays generally, and the heavy ions. For example, here I'm showing you the proton. So you can see that the pink curve, it releases its maximum energy at the very beginning, right? And whereas the red curve, we call it the Bragg peak, it releases its maximum energy at a certain depth, right? So let's say if you have a tumor, let's say if you have a tumor within like 23 centimeters inside the body, then if you use photons, that means X-rays or gamma rays, you can see that the maximum energy release at the very beginning, whereas a small dose goes to the actual tumor. Whereas if you use heavy ions, for example protons or carbon, it can release its maximum energy at that certain depth, right? So, and the other important thing is that the blue curve, it is the modified proton beam, or we call it a spread out Bragg peak, SOBP. So you can stretch the narrow Bragg peak to the whole tumor, right? So I will explain you as to how we do this in next few slides. Okay, now let me explain you the variation of penetrability with the energy of the beam. So here these are my actual results. Here I have I've used carbon 12, right? So you can see that if you use 150 MeV energy, it penetrates up to like 5 centimeters inside the body. Whereas if you use 200 MeV, it penetrates like maybe 8.5, almost 9 centimeters inside the body. So let's say there's a tumor inside the body, like 6.5 centimeters inside the body. Then what is the radiation? What is the radiation that you use? What is the energy? It's like see here, like maybe 170 MeV. So you know, according to the tumor, you know what is the radiation level, or what is the energy that you use to treat this cancer. And then I told you, now we have to give a dose to the whole tumor here. So what we can do for that, we use a modulator. So you can see that in this modulator, starting from 0, the thickness increased, right? So this is a wheel, so we can rotate this so that we can change the thickness of the modulator. So you can see that in this graph. Oops. So in this graph, so if you have 0 thickness, the radiation penetrates up to 85 millimeters inside the body, right? And now let's say, imagine that the radiation, the tumor is from like 5 to 8.5 centimeters inside the body. Then what you have to do now, you select the radiation. Now you select the energy of the radiation, and now you have to give a dose to the whole tumor. So what you can do, you you change the thickness of this modulator. When you increase the thickness, you can see that these bragg peaks shift from right to left, right? So by that way, you can give a homogeneous dose to the whole tumor. So you can see that in this picture. Where, so here this red box is, let's say it's the tumorous area. So if you use the carbon or proton radiation therapy, and if you use the modulator and spread it out, we can give a dose to the whole tumor, right? Like if it is in 3D, right? So and you can see that if you use photons, that means gamma or X-ray, you can see that the maximum energy release in the beginning. So the dose to the tumor is minimum. So unwanted radiation goes for healthy tissues and organs, which is not good, right? And also after the tumor, you can see that there will be another unwanted dose goes to the healthy tissues and organs, which is again not good. But whereas in this proton and carbon radiation therapy, the unwanted dose for the healthy tissues and organ in front of the tumor is minimum, right, compared to photons. And after the tumor, actually the very minimal dose goes to the healthy tissues and organs, right? So this is that's why this carbon and proton radiation therapy is very good and advanced method for radiation treatment. And so my interest was on carbon and proton. So you can see these two Bragg peaks. Actually, I normalized this Bragg peak so that you can get an idea about the width of the Bragg peaks. You can see that this red curve is for the proton, whereas the black curve is for the carbon. So you can see that carbon Bragg peak is much narrower compared to the proton Bragg peak. So what is the importance here? So if the Bragg peak is narrower, then it's very good when it comes to the edge of the tumors. It's kind of like a sharp knife when it comes to the edge of the tumors. So this scale goes, the width of the Bragg peak scales with a to the power minus 1/2. So A is the mass number, so obviously carbon has higher mass number, so that's why this Bragg peak is much narrower, right? So it's better if you use carbon, right, in this case, right?